everyone. Again, welcome back to the latest lecture session. So, quick review, obviously, right? So, we were discussing or talking about the aspects relevant to groundwater remediation or contaminated groundwater, remediation of contaminated groundwater, right? In that context, we are talking about something that we observe out there in the nature, and thus we call it obviously natural attenuation, right? So, let's look at what we have discussed thus far. So, we have natural attenuation, right? So, obviously in this context there were two aspects that we need to look at, let us say, or two ways of attenuation. One is the non-destructive, as in the concentration decreases, but if you look at the mass of the relevant compound, let us say in the entire system, that does not decrease though, right. So, though those were non-destructive mechanisms, let us say, and the other were the other one was the destructive mechanism, where you had what do we say biological process or such that brought about degradation, right. So, here we had two cases, one is the non-destructive and the other is the destructive. So, in this case obviously only concentration decreases, right, but in this case obviously both the mass of the relevant contaminant and thus obviously the relevant concentration decreases, right. So, again what are some of the aspects that bring about or mechanisms that bring about non-destructive or that are relevant to this particular case of non-destructive mechanisms, I guess, right. So, think of what would happen to the contaminant in the groundwater. So, let us say at this particular location you have the release of the contaminant and you have groundwater flowing in this particular direction, let us say, right. So, let us say if there was no groundwater flowing, the concentration of the relevant contaminant at this location would always be, not always, more or less be similar to what we have initially, right. But if I have groundwater flowing along in this direction, so the contaminant or part of the contaminant is going to be transported along with this particular groundwater flow, right, or advection, as we discussed earlier, I guess, right. So, in this particular case you obviously are going to have dilution, right, dilution due to the advection, let us say, right, dilution due to advection, right. So, the concentration here is going to decrease. Why is that? Because some of the mass of the compound or contaminant has been transported to somewhere else. So, the concentration, which is nothing but mass per volume, let us say, or moles per volume, let us say at this location, is going to decrease, right. So, you are going to have decrease in concentration of the contaminant, but you are not going to have decrease in the mass, the total mass of the contaminant in the system. So, and the other aspect is obviously in groundwater, what else do you have? You have soil, let us say, not in groundwater, pardon me, subsurface. You are going to have soil and groundwater. So, the contaminant which is in the groundwater, let us say, depending upon its properties, can also be adsorbed onto the relevant soil here. So, that particular case is going to be sorption. So, let us say if you have the contaminant in the groundwater and it's as part of it changes phase from the aqueous or the groundwater phase onto the soil, let us say, or is adsorbed onto the soil now. So, you are going to have less mass and thus less concentration in the groundwater, right. So, the concentration in the groundwater, you can say decreases due to sorption, let us say, right. But obviously here we are talking about the contaminant changing phase from the groundwater to the soil, but not the other way around, but depending upon the site conditions or when the release occurred of the contaminant, you will obviously have those aspects to look at too, right. So, sorption is one aspect, and I think we also looked at volatilization, right. So, let us say you have your particular contaminant, right, either as an NaPl, let us say, or such, and let us say you have a free pore airspace in your particular between your soil, right, either in the vado zone or in the unsaturated zone, let us say, right. And what is going to happen now? Let us say depending upon the type of contaminant, let us say if it is a volatile compound, let us say hydrocarbons, chlorinated solvents, these kinds of compounds are typically what do we say, that relatively volatile, let us say, right. So, they would typically want to what do we say, be in the gaseous phase. So, if a compound, let us say, is in the aqueous phase and then it comes in contact with what do we say, gas or pore airspace, let us say, the contaminant which is relatively volatile, that is the one that I am assuming here obviously, is going to try to change phase from the aqueous phase to the gaseous phase, thus leading to decrease in the relevant concentration in the aqueous phase, right. So, volatilization. And the other aspect we looked at or briefly looked at was dispersion, I guess, right? So dispersion, what is that about? So I think we had the relevant schematic, let's see, I think let me try to draw that out here again, that's better. So if this is the soil, let's say, top view, okay, and particle A enters here, you know, it can move in various directions, right, or various paths, pardon me, or it can take various paths. So a compound starting at the same location ends up at A, B and C locations, right. What is the, why is that? Because of the tortuous path, you know, that it takes as it traverses this particular soil, let's say, or the you know, subsurface media here, right. So due to the tortuosity that's inherent in this particular system, you know, the particle that starts at the same location can end up at multiple locations. So what does that mean? You have what we say dilution of the relevant or dispersion of the relevant contaminant here, thus leading to decrease in the concentration. As in, for example, instead of taking various paths, if all the three compounds that are present here ended up here, let's say, right, then is the concentration changing? Nope, because all the three moles, if I can say for now, are which were here are still here, let's say. Maybe the concentration here is decreasing, but if I look at it with respect to distance, it's not changing there. But that's not how it occurs. You know that because of the tortuosity, let's say, the relevant contaminant, you know, will take different paths, and thus you are going to see relevant attenuation of the concentration, and that's what we have with respect to, or that's what we call dispersion. So typically, let's say, in groundwater, we also look at, we will also have diffusion depending upon what we say the molecular diffusion coefficient, but typically we also consider that to be a part of, or can consider that anyway to be part of dispersion. Okay. So again, moving on to the destructive mechanisms. So obviously destructive mechanisms, as in the compound itself is actually degraded, as in the mass of the relevant compound is degraded. It's not that, you know, you have, let's say, 3 molecules here in this volume, and I remove 2 and put them somewhere else, and thus concentration decreases. That's typically what we have in the non-destructive mechanisms, right. But in the destructive mechanisms, you know, out of the 3, let's say 2 of these particular moles of this particular compound are actually degraded, let's say, right. It's not that they are changing their location or, you know, point in space, but they are actually degrading. So how does that come about? You know that similar to us, let's say the microbes want to thrive, right. So what do they want? They need sources of energy, let's say, and also energy that's used for their growth and cell synthesis, let's say, right. So they want to grow too. So what do they need for that? They obviously need an electron acceptor and an electron donor, right. Again, you know, different aspects. So we are going to talk about this in a bit more detail later, so I'll skip this for now. So in this context of the destructive mechanisms, we talked about I think natural remediation, naturally occurring remediation, I guess, right. And in that context, we also talked about some aspects like if this isn't fast enough, let's say. So I believe we slightly digress from this particular topic of naturally occurring degradation, as in we talked about biostimulation and bioaugmentation, I believe, in that context. So obviously here you or the human is, you know, has a role to play here with respect to the biostimulating the relevant biological activity or augmenting it, right. But you know, I wanted to briefly discuss that in the context of this natural attenuation. But obviously once you start playing a role and trying to fasten up the kinetics, typically though it's not naturally occurring remediation anymore, but again, as I mentioned, I wanted to discuss that in detail though. So let's have a quick recap of what we have been up to. So again, as I just mentioned, naturally occurring bioremediation, but what's the issue though? Kinetics can be an issue, and thus leading to incomplete degradation, right. So let's say again, compound A, instead of going to its end product, can, you know, form byproducts, and I think we did look at some examples earlier in the context of PRB. I think when we had PCE or TCE, and one of the byproducts was vinyl chloride, which was more toxic than the parent compound. So you can have such issues, you know, that depending upon the extent to which you have the relevant remediation, right. So biostimulation, we discussed that, and in this context we looked at the relevant graph. Again, what do we have here? We have 2 aspects, as in they are also putting in the electron acceptor or the oxygen, right, so that the biological activity, you know, increases, and they are also removing this particular gaseous compound in the gaseous phase, right, by pumping the air out and then treating it here, right. Again, I'll skip this because we looked at that. Bio-augmentation, again, you isolate microbes from stressful conditions, put them here, but again, depending upon the type of site conditions, obviously, they might not thrive, right? Again, there is a reason why the relative species that are existing right now in that site exist there, right? Because they are able to survive in that particular location, let's say, right? Okay, so let's move on. So evaluation, what are the advantages? Obviously, low cost, as in you are not putting any or not any not capital intensive or even monitoring intensive, yes, but not capital intensive, obviously. And what else? It can be applied to all or part of the site, right? So it can be applicable at different ratios of the particular area of the particular site, right? And then what else do we have here? It can be used in conjunction or together with other remediation techniques, right? Remediation techniques. So that's obviously something else out here, yes. So it can be used in conjunction with other remediation techniques, and we are actually degrading the compound. Or looking at, and importantly again, we have no above surface structures, right? So these are some of the advantages, and what are the disadvantages though, right? Obviously, as we just discussed, kinetics can be slow, leading to, again, as I mentioned or we discussed, incomplete degradation, right? And because of this, what issues do you face? Let's see, because the kinetics are slow, what does it mean? The time taken might be relatively, tens of years now, right? So what does that mean? That long-term monitoring is required. So long-term monitoring is required in this particular context. Obviously, applicability depends upon the site. If it's, let's say, if it, as in the contaminated site, is in a densely populated area where the people are taking the water from, would you rely on natural attenuation? Probably not, if not, certainly not. Why is that? Obviously, the kinetics are relatively slower, and the relevant population might be affected or by this particular contaminated soil or the groundwater. But let's say if it's due to, let's say, some mining activity, let's say, and I'm giving a very generic example here, in a relatively remote location or such, or you already have, let's say, some strata inside, in the subsurface that lead to contaminated groundwater generation, but there are no immediate users of what do we say, the relevant water or such, or exposed population in that vicinity. What would you do? Maybe resource intensive and such, but again, that's going to disturb the system again, right, or the costs, obviously. So you can look at what do we say, attenuation with respect to natural attenuation, and then put institutional controls about restricting entry to the site, or trying to see to it that this water is not used by the relevant limited population, if any, in that location, and so on, right? But again, what's the key here? The key is that long-term monitoring is required though. And in that context, obviously, you are trying to rely on what's happening in the in nature or the subsurface to get the job done, let's say. So what is required though? You need remarkably extensive site characterization, right? Different aspects, either with respect to understand the groundwater flow paths, let's say, or even, let's say, to understand what are the strata out there. For example, if you have a lot of iron, let's say, in your soil, let's say, and you have a compound that needs to be, let's say, oxidized now, right? What do you need? You need oxygen, right, for, let's say, or an electron acceptor. But you have a lot of iron in the relevant soil. What's going to happen now? That iron can, what do we say, react with the oxidizing agent or the electron acceptor, right? So there are such issues. Again, we'll look at that later. So that's something that needs to be looked at. So extensive site characterization, long-term monitoring, incomplete degradation. So these are typically the major aspects, right? Again, the other aspect is that site conditions can change though, right? So the site conditions can change such that it becomes unsuitable for natural attenuation, let's say, right? So that's something obviously you need to be considered, as in you are looking at, let's say, tens of years or maybe 50 years or so, let's say, in this particular relatively remote area, let's say, but your particular analysis, let's say, is based on the current conditions. But let's say the site conditions changed, obviously that's going to be an issue. It can be faster, but obviously it can also mess up the relevant system out there and decrease the kinetics further here, right? So let's move on to the mechanisms of biodegradation now, right? So mechanisms of biodegradation, how and why, let's say, do they occur? So obviously one typical aspect is the aerobic process, right? And obviously most people are aware of the term aerobic process again, right? So again, typically what are we looking at? We are looking at, what do we say, the presence of oxygen or the degradation of the relevant compound in the presence of oxygen here, right? So again, I understand they are generic terms, but obviously with relevant knowledge of the basics, you should be able to do better. So what's the role of this oxygen? As we mentioned, it's an electron acceptor, right? So again, what's the key here? Let's say we have that oxygen and you have your organic compound which is, let's say, your contaminant, right? And they can go to, let's say, if it's complete degradation and mineralization, CO2 and H2O and energy, let's say, right? And this energy is required by the microbes for their growth and cell synthesis, let's say, right? Obviously they need carbon. Again, carbon can be from this particular organic compound, and you also need other nutrients, but they typically exist out there in the nature, in the soil, or you can add them obviously. But again, what's the driving force here? The microbes want to grow, right, or thrive obviously, and for that they need energy, and for that they look at sources of electron acceptors and donors. So what are the electron acceptors and donors in this context though? Here this obviously oxygen is the electron acceptor, right? And the organic compound, and this obviously organic compounds, there are many what do we say, kinds. So we are talking about the one that can act as a electron donor, right? So the electron is transferred from here to here, let's say, right? And in that process energy is released, yes, and depending upon the extent to which the degradation goes, you end up with CO2 and H2O as your end products here. So in an aerobic process, obviously we are talking about a redox process where you are talking about oxidation of the relevant compound, let's say, in the presence of oxygen or by oxygen, let's say, right? And again the energy, how do the microbes fasten this door? How do the microbes facilitate that? So they release enzymes, let's say, which act as catalyst here, right? So if there are no microbes and let's say you conduct this experiment in the lab, let's say, and look at or put in that organic compound and oxygen and look at it or the rate of this particular reaction, the kinetics might be way too slow. But let's say if you have the microbes, obviously because they want to get energy, they release these enzymes which can what do we say, facilitate or fasten the kinetics of this particular process. So this is the what do we say, general outline, let's say, right? So but let's say, let's look at one particular aspect. Let's say this is my side view, and then I have, let's say, an underground storage tank, let's say, right? And this is something we talked about. I think we have a couple of slides here. So here let's say I have an underground storage tank, and the relevant compound has, what do we say, been released. Underground storage tanks typically used for hydrocarbons or petroleum compounds and such, or even let's say depending upon the type of industry, for safety reasons and such, and obviously for economy too, they have economy of space, I mean, they are going to have these underground storage tanks, let's say, right? So but these typically develop leaks, and let's say your contaminant has has been released, and now you have it, some of it in the gaseous phase, and obviously you see this particular contaminated plume though, right? So assume that we are not having this air being supplied or such, right? So you have these hydrocarbons C and H typically, right? Hydrocarbon, petroleum and diesel, they are hydrocarbons obviously. So C and H, as you see, what do we say, H is relatively more electropositive, right? It does not want to pull the relevant electrons towards itself. So carbon is relatively more electronegative compared to hydrogen, and that's why the electrons, let's say, are drawn towards the carbon, and carbon here in this context of the hydrocarbon, let's say, is relatively more electronegative, or it's reduced, right? So again the key here is that in the hydrocarbons, the carbon is typically in the reduced form, right. So, obviously, what is it that you are trying to do? You want to oxidize this reduced compound, and how do you do that? You need an electron acceptor, right. So, the key here is that if you do not provide air, what is going to happen to the system? So, this is your hydrocarbon contaminated plume, let us say, okay. And where is the degradation going to occur? Let us say, is it going to be the edges, center, throughout the plume? Where is it though? So, if you look at it or think of it, for the redox process to go through, what do you need? You need the electron donor. The donor is available. What is that? That is the hydrocarbon though, right. The donor is available, but you need an electron acceptor. In this case, let us say we are talking about oxygen here, right. So, where is the electron acceptor available? It is not available, let us say, throughout this particular plume, as in initially if you had any oxygen present, that would have already been consumed, let us say, or such. So, the degradation is only going to typically occur at the edges of this particular plume. Why is that? Because that is where you have both the electron acceptor oxygen and the electron donor, the electron donor, the hydrocarbon, and the electron acceptor oxygen in contact. Where is that? Obviously, typically in the periphery of your particular hydrocarbon contaminated plume, right. So, again, why is that? Because you need both the electron acceptor and donor in contact, let us say, or in proximity, let us say, or they need to be bioavailable, if I can use the term, let us say, for the relevant degradation to occur, right. So, obviously, if it is only occurring at the periphery, obviously the relevant degradation is taking place only at the periphery. For that to fasten that, what can you do? Obviously, one aspect is to pump or provide or stimulate the process by adding oxygen, let us say, or air. That is what this particular graph is about, right. Again, that is with respect to the relevant aspect out there. So, we are done with that. So, obviously, we looked at an aerobic process. So, let us move on to looking at anaerobic process, let us say. So, obviously, let us say when anaerobic process, we are talking about systems that go through or take place, let us say, in the absence of oxygen. So, coming back to our example earlier, let us say you had limited oxygen and all that oxygen was consumed, let us say, right. So, do you think the degradation can still occur or not occur though, right? It can occur, but obviously, it as in the hydrocarbon still needs an electron acceptor, right. So, we are continue with the other case. So, we have petroleum products or the hydrocarbon contaminating the groundwater, and earlier you had oxygen, but now you have no more oxygen, right. So, what do you still need? What was the role of oxygen though? The role was that it is an electron acceptor. So, now you need a alternative for the electron acceptor for the redox process to go through, as in you already still have a lot of electron donor, which is your contaminant in this case, right, and you are looking for the electron acceptor. So, what are the typical acceptors out there and how does it go about? So, again, in this context, we call this process to be respiration, let us say, respiration. And what is it typically about? You have an electron donor, which is in this context typically your contaminant, let us say, typically, but maybe let me not generalize right now. So, you have the microbes trying to look at degradation by using the electron donor and electron acceptor, let us say, and then that going to the relevant CO2 and H2O and energy, let us say, right. So, again, transfer of electrons, you have this particular case, and the microbes use the energy, but here let us say in this context of the anaerobic process, you do not have oxygen anymore, right. So, what are the other electron acceptors that you typically come across or such? So, typically let us say you have nitrate or nitrite. Again, oxygen is relatively more electronegative. Again, that is why you see that nitrogen is relatively more oxidized, right. So, again, nitrogen here in these forms is relatively more oxidized, and then you can look at ferric iron, Fe3 plus, let us say, right. That is also in its oxidized form. And what else can I look at? Let us say, I think I can look at sulfates, SO4 2-, right. I can also look at carbon dioxide, let us say, right, carbon dioxide, and then I can look at RCl, let us say, right, carbon dioxide and so on. So, these are the other typical electron acceptors, let us say, that can be looked at in the particular situation now. So, we look at each of these because they are important. So, let us say if there is no oxygen and all these compounds are present, let us say, in your particular water. So, which one would your particular system choose now? System as in the microbes choose as the electron acceptor to degrade the relevant compound, let us say. which let's say in this case is your electron donor, let's say, right? Which one would you choose? For example, if it's you, let's say, what would you choose? You would choose the option that would give you the greatest benefit for the lesser amount of work, if I can say that, or I think the idiom is greater bang for your buck, right? So in that context, you are looking at the microbes getting energy. So they'll look at or choose that particular acceptor which will give them greater energy, right? So typically, let's say oxygen is somewhere out here. If all these compounds or electron acceptors are present, microbes will choose oxygen, let's say, as their electron acceptor. Why is that? If you look at the delta G values or such, greater energy is released, when let's say oxygen is used as the electron acceptor, let's say, right? Again, it's obviously relevant to thermodynamics, but I'm not going to look at that here though. So if electron acceptor or the oxygen is not present in this context and you are looking for other electron acceptors, it will choose the next particular option which will provide greater energy, let's say, right? And that typically is the nitrate and nitrite, let's say, right? And people might have heard of denitrification and such and facultative bacteria. I think in relevant biological or wastewater treatment plants, you also need to look at removal of nitrogen, let's say. What do you typically do? You have ammonia, let's say, NH4 plus, they oxidize it to, let's say, nitrate, let's say, right? And then this is nitrification, and then denitrification to, let's say, I think N2, or sometimes the oxidized form of this N2, let's say, right? Again, typically, this is what can happen. So here too, after your particular degradation, this can form, let's say, nitrogen gas. And again, what types of microbes? I think people might have heard of facultative microbes. So let's say if there is oxygen present, they will use oxygen as the electron acceptor. If oxygen is not present, for the electron acceptor, then they will use these nitrates, let's say, oxidized forms of nitrates, let's say, and typically the end product is N2. And here, let's say, then if these nitrates and nitrites are not present, what will be used, or what will be the next preferred electron acceptor? You are going to move on to iron, let's say, ferric iron, and that can be degraded to or reduced to Fe2 plus here, right? Keep in mind that these are acting as the electron acceptor. Obviously, if Fe3 plus accepts an electron, what's it going to transform into Fe2 plus, right? And again, SO4 2 minus, once it's oxidized, it can go to the hydrogen sulfide, which is more reduced form of sulfur. Obviously, sulfur here and oxygen, relatively more oxidized form of sulfur, and here sulfur and hydrogen, so thus relatively reduced form of sulfur. And CO2 can be, what do we say, CO2 itself can also act as an electron acceptor and be degraded to CH4, let's say, or reduced to CH4. And then comes this particular, at the bottom of this particular chain. Why is it at the bottom? Obviously, because it gives relatively the least energy when compared to the other electron acceptors, when the electron acceptor is involved in a redox process. So here we have, this obviously I am using for denoting the chlorinated, obviously because they have chlorinated solvents, let's say, or chlorinated organics, pardon me, let's say chlorinated organics, right? So you have the chlorinated organics, let's say, that can be further degraded or reduced now, right? Here they are relatively oxidized now, and they can act as electron acceptor. So if you have, let's say, PCE or TCE, let's say, and you have oxygen present in your particular system, will the degradation take place? Let's say if you provided some organic compound. Let's look at this particular scenario, as in, let's say I have the petroleum or the products or the hydrocarbons, let's say, hydrocarbons, and I have, let's say, PCE or TCE, oxidized form, let's say, chlorinated organics, right? These are obviously the more, what do we say, oxidized forms, right? So if there is oxygen present, what's going to happen to the system, or which one would the microbes obviously prefer to degrade, let's say. So in this case, obviously what would be degraded? Petroleum hydrocarbons will be degraded, because oxygen can act as electron acceptor, this can act as electron donor, and then the degradation is going to take place, let's say, right? But is PC or TCE going to be degraded in this case? Obviously not. Why is that? Because the microbes want greater energy, right? And obviously, by using oxygen as the electron acceptor, they get more energy thus. But if there is no oxygen and none of the other electrons acceptors we have discussed, let's say NO3, Fe3 plus, SO4 2 minus, CO2 and so on, let's say, And then what happens now? Then this is still your electron donor, and this is your electron acceptor, and then you have the transfer of the electrons here, and then degradation, let us say, right. So, that is what occurs. So, for your particular let us say chlorinated organic to be degraded, right, here the role is that it plays the role of an electron acceptor. There should be no other competing electron acceptor. So, that is the key here. So, even if you do not have petroleum hydrocarbons, what can you do though? You can add some other organic compound, let us say, right, to your system that can act as an electron donor, that can then provide the electrons to this PCE or TCE, perchlor or tetrachloroethylene, I guess, right, and then that goes to degradation. So, these are the aspects that you need to keep in mind, at least when you look at the initial analysis, as an does it make sense when I say that the microbes can degrade the relevant compound in this particular site or these conditions, right. So, that is one particular aspect to look at, right. So, the other aspect or that I would like to point out is that you have fermentation, let us say, right. So, what takes place here, let us say you have an organic compound, and from here you from the same organic compound you have what to say the formation of a more oxidized form and a more reduced form, right. So, here your electron acceptor and donor, they are not two distinct compounds here. So, here we are looking at one organic compound, and that turning into or transforming into two parts, one of which would be more oxidized and the other one would be the more reduced form. So, let us say I have CH3COOH that can go to CO2. So, this is the relatively more oxidized form, as you can see here, and you can also have CH4 formation. So, obviously I am not balancing the relevant stoichiometry, I guess, right, or is it already balanced? Yes, it is balanced, I guess. So, here this is the more oxidized form of carbon, if you look at this here, and this is the more reduced form, as you can see from this particular carbon, right. So, fermentation, I guess, right, and again the relevant process, yes, takes place. So, again all these processes that we have looked at are part of these metabolic process, right. The aerobic and aerobic process that the microbes look at, or the anaerobic process or the respirations that we look at, or the fermentation, what are they about, or how do I have a term for trying to understand all these terms. They are involved in the metabolism or in the metabolic process of the relevant microbes. Let's see, even we have our own metabolic process, and they are obviously involved in generating the relevant energy for our particular system, right. So, in this context, obviously we have other examples too, I guess, C6H12O6. So, I am not balancing this, can go to CO2 plus H2 if I am not wrong, let us say, right. And so, the key here is that you have another particular interesting compound that is being formed here, that is hydrogen here, let us say. And hydrogen, let us say, is worthwhile in your particular subsurface because let us say that itself can again act as an electron donor here, let us say, right. So, that acts as a reducing agent here, yes, and some particular microbes, or quite a few at least in the subsurface, are very particular about what their electron donor needs to be. And so, typically let us say even though this process is not what would let us say add value to your system, people try to promote this because you need to have, or they want, let us say, hydrogen in the system, let us say, if not from this compound, from other compounds they want to have hydrogen producing substances. Some of them are called hydrogen producing substances. So, H2 is tried to be promoted in the particular system, let us see, right. Again, these are different aspects, but looks like I am running out of time. So, we will move on to what we say the relevant aspects in the next class, and they are typically about natural attenuation. I am saying all this occurs, but how do I prove, let us say, that it is occurring, or what are the aspects that I need to look at, right. So, with that I am done for today, and thank you.